All right, let's keep thinking about this building block function that's identically 0 and then vanishes to infinite order and then goes up. And we want to prove it's smooth. Well, look at the pattern so far. F of x, of course, is interesting and 0, interesting 0 for f prime of x. And interesting is a polynomial in 1 over x times e to the minus 1 over x. And I claim this is also going to be a polynomial in 1 over x. And, of course, 0 for x less than or equal to 0. We've already figured out, we did do the careful analysis to show that this really is 0 at x equals 0. And the claim I want to make is that this is some polynomial in 1 over x times e to the minus 1 over x. And the key there is that we talked a little bit about L'Hopital's rule, saying that we know how to take this kind of limit. Okay, so we're going to make that into an inductive argument. We're really going to say that this is true for the nth derivative. So it's clearly true for the base case, and we did a little bit more than the base case. And so we're going to assume that the nth derivative of x is some polynomial called Pn applied to 1 over x times e to the minus 1 over x whenever x is greater than 0. And we know that we're okay for x less than 0, and then we'll make sure that this makes everything work for equals 0. Okay, so just take the derivative of that. It's really not hard. Product rule and chain rule. Product rule, you get the derivative of this guy. So that's the derivative of a polynomial, which is going to be a polynomial again. But then times the chain rule, a minus 1 over x squared can miss out. This one's unchanged. Then plus the Pn of x unchanged, times, we already found the derivative of that guy, 1 over x squared, e to the minus 1 over x. Okay, and so the new polynomial, we even get an explicit formula for it. P sub n plus 1 of y, let's say, is, we're getting minus y squared Pn prime of y plus, ooh, there's a 1 over x, I forgot here. It's all applied to 1 over x. Plus Pn of y also times, but now positive y squared. Okay, because this is that polynomial applied to 1 over x. And this is clearly a polynomial, that's the main thing. Okay. So we assumed that it was a polynomial 1 over x times e to the minus 1 over x, and then the next derivative is of the same form. Okay, so inductively, this is something we can say is true. We didn't particularly care so much about what happened as x greater than 0 in terms of explicit formulas because we knew it was differentiable. But we need to have some control over what this formula is in order to take the derivative at 0. So now we're up to, that was part F, by the way. Now we're at part G. Okay, so now one more induction. The claim is that the nth derivative at 0, where we have to really think about it by the definition, exists and, by the way, is equal to 0 for all n. Okay, the base case has been done and then some, and so we're going to assume this is true, and then we're going to try and see for some n, and then we're going to look at it for n plus 1. Okay, so the nth plus 1 derivative at 0, have to go to the definition. Again, the minus from the left, it's obvious, so we just have to worry about from the right. And so this is the limit as h goes to 0 plus of the nth derivative at h minus the nth derivative at 0. Aha, that's where we use the induction hypothesis. And we need to know not just that it exists, but we really need to know it's 0. So we can put it in here. That goes away over h. And now we use this part of it. We want to use the need to use the explicit formula to some extent. We don't need to know exactly what that polynomial is. Okay, so that's going to be 1 over h times an nth degree polynomial in 1 over h. Oh, I'm seeing a typo already. I should have changed an x to an h. Oh well, when I look at my cheat sheet here. Okay, well that's still a polynomial in 1 over h. And so the same deal, let's just go up here. Just do one more change of variables to make it really clear. Y equals 1 over h again. Is that fitting? Yeah. Okay. That's y, p sub n of y. That whole thing is a polynomial. might have a fairly high degree. It might take a while for this to actually achieve the limit we claim it does, but it's going to be equal to 0. This is a polynomial being dominated by a decaying exponential. So now finally, we're done. We now know that f of n of x exists for all x, including 0, which is the interesting point, and all n, I guess x in R and n in the natural numbers. Okay, so in particular, f is smooth. That was the main punchline we wanted. So we've found a smooth way to join identically 0 to interesting and non-zero, and that's a really big deal that exists. Okay, so let's go back though to what's kind of weird about this. This is often presented, if you don't have a use for it, as a pathological example. It's like, ooh, beware, this is weird and bad. It's an incredibly useful function, but part H is about remembering what we were talking about in the previous video in number 1, the Maclaurin series, just the Taylor series at 0, for this function f, well, remember a sub k is that kth derivative at 0 over k factorial. Those are all 0. Okay, so the Maclaurin series is the sum of a bunch of zeros times x to the k. That's 0. So we kind of knew to expect this, though, from number 1. We knew that we couldn't get this kind of behavior at all with a 0 on a big set from a non-zero function that was analytic. And so this is confirming that if you try to take the series, which you usually expect for a smooth function to reproduce the function, for e to the x and cosine and sine, you get used to this idea when you study series in calculus, that smooth functions typically get reproduced by their series. Well, the series, let me do another color, the series just says, I think this is the 0 function, as far as I know, as far as I can tell by evaluating derivatives at 0. So in the supplement, I'll talk about how that doesn't contradict Taylor's theorem, because a not very careful understanding of Taylor's theorem seems to say that any smooth function is given by its series, and that's not really true. That's not what Taylor's theorem says, and this is a great example to get more understanding of that. But it's not super necessary for what we're doing with distributions, so I'm going to put it in the supplement. Okay. Now, this was just a building block. Let's go on to 3. Let's do some stuff. It's not nearly as subtle, but it's kind of creative, and you can get tripped up on it a little bit. We want to create smooth functions to order, basically, with various desirable properties. The main thing we're going to really want to get to by the end of it is an analog, a smooth version of a step function that's non-zero in some region and 0 outside. And this certainly has compact support, but it's not smooth. We'd like to round it off. And the key thing is, if this is going to be a test function, it needs to be infinitely differentiable. Remember why that was true? Why did the test functions need to be infinitely differentiable? That was so that we could take derivatives at will of distributions and never worry that we were just breaking the basic theory. Okay, so we want to take a mesa like that, a step function, and smooth off all those corners. And that's going to just take a few steps to go from this one, which was 0, and then non-zero but not particularly well controlled values, to go to here. Okay, so A, and this is a good one even if you need hints on one part of it, if you're stuck on one part of it, is to only look at the solutions or watch these videos to get a hint on that, and then stop and try to go back to the other one. Okay, what we want is, the first one is G. We want to have support in the unit interval. This guy was not yet compactly supported. It was 0 this direction, but it's not 0 anywhere here. And the first thing to do is to actually get any test function. This will be our first example of an honest-to-God test function, a smooth function with support in a particular finite interval. Okay, and so let's think about how to do that. This is f. This vanishes when you go to the left. It's not hard to create something that vanishes when you go to the right. Just flip it. And in fact, what I'm going to do with the 1 minus x, I'm going to guarantee that I get something that vanishes after 1. Okay, so that's a flipped version. And then you just want to think about how can you combine two numbers, f of x and f of 1 minus x, so that zeros are really easy to create. And in particular, so that if either of these individual pieces are 0, you get a 0 out. And one of our favorite arithmetic operations has that property. So this is a really good way to do it. There's many, many ways to do these things, and we don't have to start with this particular function f, e to the minus 1 over x, but this is sort of the standard, simplest way to create these guys. The main thing is that we're doing an existence proof. There is such a gadget, period. And we're not incredibly interested in the exact values. Really, in fact, compactly supported smooth functions there's so many of them. They're actually a huge, huge number of them. They're not actually that special. It's just that we get locked into this idea that everything's given by analytic functions, basically, or minor modifications of them, that makes us think that they're weird and pathological. They're actually really quite common. Just hard to write formulas down for, but we've managed it. We need a little piecewise thing, think about limits, stuff like that. Okay, so now B, this is a pretty easy one. Just to show the flexibility here, we want HAB of x to be a version of that, but just again, a little bit more made to order, where it's supported in AB. So it's certainly compactly supported. Okay, and that's a very standard thing. We had this guy between 0 and 1. I can just shift it and scale it. Okay, so I'm going to take G, and I'm going to look at it. I'm going to shift it so that it starts at A, and then I want to scale it so that the 0, 1 length becomes the length B minus A. And just dividing by B minus A is good. You can check that. If x is less than A, this is all 0, or this is negative, and therefore you're going to have a 0 value from the G function. If x is greater than B, then this is bigger than 1, and you're going to get a 0 from the G function. So there's our H. That's a lovely building block. So that's exactly what I've been drawing all the time, a test function, one of these thermometers, something that can be localized arbitrarily well. A and B can be arbitrarily close together, and we can get a little test function. We could even make it have unit. It's often useful to have unit area if we want, by just dividing by its integral. Okay, not something I asked for, but definitely useful. Okay, now next thing is I want the thing I don't have here is control over the values, and I'd like to go back to this guy. This kind of looks a little bit like a step function, but it doesn't go up to a specified value. It asymptotes to 1, but I'd like to actually nail 1 here. Okay, so that's why we want this function. Ooh, k. Ooh, I have lots of typos in the solutions. I really gotta do this. Gotta fix this. So we want k of x. I copied this in from a later problem. When x is less than or equal to 0, I want k of x equal to 1 if I'm beyond 1. So I want to actually go up and hit 1 for real. And then just to have nice control over it, let's say it doesn't go up too far or go negative or anything like that. Let's say that it's strictly between 0 and 1 when x is between 0 and 1. Okay. This is a little trickier to do, but it's all just based strictly out of f. Okay. So we want to take that function f and go like this. Well, it seems like a multiple of f would be a good idea, because that's going to guarantee it's 0 here. But then we also need something that turns on its activity at 1 and does something super special this way. So 1 minus x, f of 1 minus x, also seems really crucial as well. So we want something that takes f of x, and it doesn't really need to modify it here, but it could. That'd be fine. Modifying a 0 is not going to kill us. And then we want it to equal 1 out here. Well, I'll just give you a hint. One of the ways to get something to equal 1 is divide two equal quantities. So we are going to take f of x, If we divided that by f of x, we would have 1. Okay, but then we want to make sure that over here, we're not just dividing by 1, and that's where the f of 1 minus x comes in. Okay, so that is our k of x. I think that's one of the that's maybe the trickiest one, I think. It's one I have to think about to remember, definitely. So when x is less than 0, less than or equal to 0, this dies, and this doesn't, so you're not taking 0 over 0. And when x is 1 or greater, then this dies, and you get 1. And these are all positive quantities, so I'm going to positive quantity over a bigger positive quantity when I am between 0 and 1. And so it has all these properties. Very cool. I think it's very pretty. Okay. So there's our smoothed version of a step function. Okay. And then, of course, we can shift and scale that sucker. Part D is just a shift and scale version of that. And, ooh, again, I was a little. So we want 0 for x less than or equal to a. I want it to be turned on fully when it's greater than equal to b. And I want it to be in between. I want it to be in between 0 and 1. And that's just this shifted and scaled version. Exactly. It's kind of combining two ideas we've already seen. So you just shift it so it starts at a instead of 0, and then scale it so it gets to fully turned on at b. Okay. So there's our, and so this is 1. And it's not asymptotic. It's really honest to God equal to 1 by the time you get to b. Okay, it hits it exactly at b, actually, just by construction. Okay, so now finally we get to our really nice function. So we're going to have a and b and c and d. We want it to turn on at a, or between a and b, and then be fully on at b, start turning off at c, and then be fully off by d. That's what we want. We're going to call that rho for new fancy version, Greek letter version of the rectangle function. It's really our rectangular pulse smoothed out. Okay, and here's what we want, just written out. It's supposed to be 0 if I'm before A or after D. It's 1 if we're between B and C. And it's always between 0 and 1, and it's strictly, just to be very nice and well controlled, strictly between 0 and 1 if I'm in this region, the startup region, or the ending region. Okay. And really, it's just combining the ideas. To construct this guy is pretty easy. The main thing is to realize that 1 minus like LAB of x will be something that turns off. And we've already experienced that with like rectangle functions. That goes like that, A to B. Okay, so if you combine that, so let's actually use CD because that's where the turnoff is going to happen. Okay, and then if A and B are over here, we've got something that turns on between A and B, and we know how to combine those. It's just exactly what we did just a few minutes ago to create G, I guess. So rho A, B, C, D of x, it's going to have all these subscripts to tell us exactly where it is. You combine your turn on with your turn off. It's just a smooth version of what we did in a very early video of combining some step functions turning on and off to create a rectangle. Okay. So it's not super crucial, all the details. I mean, if you expanded this out in terms of all the algebra and e to the minus 1 over x's, it would look horrible. But the main thing is that it is a smooth function, infinitely differentiable, that has all the properties required. In particular, it's compactly supported, positive, has some nice control over where it has certain values. Okay. Ooh, great time to stop. It's gotten kind of long.